Hey, my name is Jan Ketil Rød and I am a professor in Geographical Information System and Science at the Department of Geography, Norwegian University of Science and Technology. And this video is the third video about map projection and coordinate system. And this video is about Cartesian coordinate system. Most of the content is taken from chapter 4 in the Norwegian textbook GIS Tools to Understand the World. So the content of this video is UTM, the Universal Transverse Mercator. What you need to know about it, what might be nice to know, and perhaps what we may call some fun fact about UTM. Now we've been through the geodetic reference system, geographical coordinates systems, and about map projection. And this video then is about coordinates on a flat map. But talking about UTM, that is indeed a Cartesian coordinate system, but it's also a map projection. So we will visit some of the principles of map projection. The Cartesian coordinate system, this comes from the philosopher René Descartes. We can distinguish between transversal and normal cylinder projection. And a normal then is when the cylinder is vertical, the cylinder is wrapped around equator. The transversal is horizontal, where the cylinder is wrapped around the poles. And perhaps not a surprise, as indicated by the name, UTM uses a transversal cylindrical projection. So secant is what we can call the line where the cylinder is tangent to the Earth model. In a normal cylinder project, the secant is typically equator, whereas in a transversal cylindrical projection, the secant is a meridian. And we notice from the lecture about map projection, looking at a normal cylindrical projection, such as the Mercator projection, the errors were small along equator, but towards the North Pole and towards the South Pole, the error increased. And therefore, land areas were becoming very huge towards the poles. This is also true for the transversal cylindrical projection, but then the arrow propagation goes east-west. So similarly as the Greenland were becoming large in the normal cylindrical Mercator projection, South America would become great using a transversal cylindrical projection. So the principles with tangent map projection, you have the secant here, is that the arrows are small on or near the secant, where the cylinder is tangent to the Earth. But the error increases, and for any map there might be tolerance limits, and when this tolerance limit is exceeded, one typically then make a new map projection. So you establish new secant and then a new map projection. UTM does not use a tangent map projection. UTM is a cutting projection. And that is a smart thing, because then the tolerance limit is becoming larger. So we have then not 1 secant, we have 2 secant line for cutting map projection. And this enlarges then the area for where we have low errors. So the tolerance limits are becoming wider. So let us wrap up some of the characteristics with a universal transverse Mercator. It is a type of cylindrical projection, transverse Mercator, because the cylinder is wrapped around the poles, not the equator. It is implemented as an internationally standard coordinate system, so it's used all over the world. initially devised as a military standard. It uses a system of 60 zones, thus there are 60 projections. And I'm not sure if I got this number here correct, but the maximum distortion is rather low. So this is why I say that you can measure areas and distances accurately whenever you are within a UTM zone. The UTM zones are each of 6 degrees of latitude, and since it is 360 degrees, we have thus 60 zones in total. And each of these 60 zones defines a different map protection. We also have zone belts, and these are then 6 degrees wide and 8 degrees tall. For Norway, we start then on 56 degrees north and interval 8 degrees north. We got new zone belt at 64 degrees north, and it goes up to 72 degrees north. And east-west, we have then peculiar thing here with a 32 VV, but otherwise it's 6 degrees intervals towards the east for each of the belts. Then for Norway, there are some peculiar things with the zone belts. Each of the zone belts are 6 by 8 degrees, but Norway, there are exceptions. Here north at Svalbard and on the western coast of Norway. And why is zone 32V wider? There was an article in Photogrammetric Engineering and Remote Sensing, October 1999, by Clifford Mugnier, which provides the answer. The UTM system was developed by US Army engineers in the early 1940s. The coordinate system used at the start of the Second World War contained many zoning divisions, which made the calculation for the military engineer very complicated. Calculations that are now easily done with computer power were then described as a nightmare. To avoid the hassle of zone boundaries at the time of much German submarine activity here along the southern coast of Norway, zone 32V was extended westwards. Then the calculation for the military engineer became easier, and they saved a lot of valuable time. So there are two practical issues with UTM. The first one is about geodetic reference frame or system, what we previously called datum. And the second is reprojection from, for instance, UTM 33 to UTM 32. Now the first issue is that UTM, since it is a worldwide system, it can be based on different ellipsoids and different geodetic reference system. And this is a slide I also used for another video when I talked about the WGS84, the ellipsoid. It is having a very similar ellipsoid which is used in Norway and the rest of Europe, called the European Terrestrial Reference System, or EUREF 89, and UTM can be based on both of these. But as you may have other data which are national data from Norway, and you may have global data which are based on VGS84, they may not align perfectly together. So my advice would then be, whenever you have global or regional data based on UTM, but on the ellipsoid WGS84, you should reproject them to be using ETRS 89. The second issue is that in Norway, when we have national data, these are typically provided in UTM 33. But this is actually a compromise, as Norway is a country with larger, huge west-east extension. So if you, for instance, are working on data on the southwestern part of Norway, or in the northern part of Norway, you have a different UTM zone than 33. And I always recommend you to use the same coordinate reference system when working with data from different sources. So if you, for instance, then are using data from the southern Norway and you have having some national data, make sure to reproject those in UTM zone 33 to those in UTM zone 32, so you have one common coordinate reference system. So this was the end of the video about Cartesian coordinate system. If you want to watch it again, and if you haven't done so yet, you should also watch the video about the geographical coordinate system and map projection, because then you may then benefit more from watching this video.